Hello, viewers! Welcome back to Dr. Carminati's YouTube channel, where we unravel the mysteries of science and technology to inspire your curiosity. If you're new here, I'm so excited to have you with us. Today, we're diving into the mind-bending world of quantum cloning, a concept that challenges the very laws of physics. Before we get started, I'd love for you to join the conversation. Drop your ideas for future videos in the comments, share your thoughts, hit that like button, and subscribe with the bell icon so you never miss an update. Let's build a community of explorers and thinkers together. Are you ready to venture into the quantum realm? Let's jump in. Imagine trying to make an exact copy of a secret code, but the moment you want to read it, the code changes. That's the kind of challenge we face in the quantum world, where the rules of physics defy our everyday intuition. Quantum cloning sits at the heart of this strange universe, blending the promise of futuristic technology with the unbreakable laws of nature. As a cybersecurity professional passionate about quantum mechanics, I'll guide you through what quantum cloning is, why it's both fascinating and frustrating, and how it impacts fields like cryptography and computing. Whether you've never heard of quantum mechanics or you're a tech enthusiast, this video will break down the concepts step by step and spark your curiosity to explore further. Let's dive into the quantum deep end and uncover the secrets of quantum cloning. Quantum cloning attempts to create copies of a quantum state, a fundamental concept in quantum mechanics that describes the condition of a particle, like an electron or photon, using a mathematical object called a qubit. A qubit differs from a classical bit, which holds a value of either 0 or 1. Instead, a qubit exists in a superposition, meaning it can be 0, 1, or both at the same time, represented by a combination of probabilities. For example, a qubit might be 70% likely to be 0 and 30% likely to be 1 until you measure it, at which point it collapses to one state. This superposition makes quantum systems incredibly powerful for computing and cryptography, but it also introduces a significant hurdle, the no-cloning theorem. The no-cloning theorem, established in 1982 by physicists William Wouters, Wojciech Zurek, and Dennis Deeks, declares that you cannot create a perfect copy of an arbitrary, unknown quantum state. Let's break this down with an analogy. Imagine you have a mysterious box containing a spinning top. You don't know its exact spin direction, but you want to make an identical box with a top spinning the same way. In the classical world, you could measure the spin, replicate it, and make as many copies as you want. But in the quantum world, measuring the top's spin changes its state due to the act of measurement itself, a principle tied to the uncertainty of quantum mechanics. This means you can't know the exact state to copy it, and any attempt to copy it without knowing the state fails to produce a perfect replica. So, what is quantum cloning if perfect copying isn't possible? Quantum cloning refers to the process of creating approximate or imperfect copies of a quantum state. Researchers like Buzek and Hillary demonstrated in 1996 that while perfection is unattainable, it is possible to make copies with a certain level of fidelity, indicating how close the copy is to the original. They introduced the universal quantum cloning machine, which produces copies with a fidelity of 5/6, or about 83.3%. This means the copies are pretty good, but not identical. The machine works by coupling the quantum system you want to clone with a larger auxiliary system and applying a unitary transformation, a mathematical operation that preserves the quantum state's properties, to create approximate copies. Let's explore how this works in practice. One method to achieve quantum cloning involves quantum teleportation, where a quantum state is transferred from one location to another using entanglement. Entanglement links two particles so that the state of one instantly affects the other, no matter the distance. In telecloning, you first create local quantum clones of a state, then teleport those clones to a remote location. This process avoids errors from quantum channel decoherence, which often degrades quantum states during transmission. Another method uses nuclear magnetic resonance, a quantum information processing technique. In one experiment, scientists passed 3 qubits through a circuit, entangling them, and transformed the second and third qubits into clones of the first with a fidelity of 5/6. Stimulated emission offers another fascinating approach. In this method, a 3-level system with 1 ground state and 2 degenerate states interacts with an electromagnetic field. A single photon stimulates the system to emit additional photons, creating clones. The photons vary in polarization, but the system ensures equal probability for each type, making it a universal cloning machine. Researchers have also employed ion trapping techniques to clone quantum states of ions, And some experiments utilize spatial light modulators to manipulate photon states, particularly for high-dimensional cloning involving orbital angular momentum. But why does the no-cloning theorem exist in the first place? It stems from the linearity of quantum mechanics. If you try to design a universal cloning machine, a device that copies any unknown quantum state, you run into a mathematical contradiction. Suppose you have a qubit in a superposition state, say a combination of 0 and 1, and you want to copy it. You start with a second qubit in a known state, like 0, and apply a unitary operation to duplicate the first qubit state. The problem arises when you test this operation on different states. The math shows that a single operation cannot consistently copy all possible quantum states, proving that a universal cloner violates quantum mechanics. This limitation protects the uncertainty principle, a fundamental concept in quantum theory. If you could clone an unknown quantum state perfectly, you could make infinite copies, measure each copy to arbitrary precision, and bypass the uncertainty principle, which states that you cannot know both the position and momentum of a particle with perfect accuracy. The no-cloning theorem prevents this, ensuring quantum mechanics remains consistent. It also blocks superluminal communication, faster than light signaling. If cloning were possible, you could use entangled particles to send messages instantly, violating relativity. The theorem shuts down this possibility, preserving the laws of physics. While perfect cloning isn't achievable, researchers have developed various types of quantum cloning machines for specific purposes. The universal quantum cloning machine copies any state with the same fidelity, regardless of the input. Phase covariant cloning focuses on states with specific properties, like those on the equator of the Bloch sphere. A visual representation of a qubit's state, achieving slightly higher fidelity for those states. Asymmetric cloning machines create two copies with different fidelities, allowing a trade-off where one copy is more accurate at the expense of the other. Probabilistic cloning machines, proposed by Duan and Guo in 1998, aim for perfect copies but only succeed with a certain probability, often using measurements to filter successful outcomes. Quantum cloning has profound implications, especially in cryptography. Quantum key distribution protocols, like BB84, a quantum key distribution (QKD) protocol developed by Charles Bennett and Gilles Brassard in 1984, rely on the no-cloning theorem for security. An eavesdropper cannot copy a quantum key without disturbing the original state, alerting the sender and receiver to the intrusion. However, imperfect cloning poses a risk. Attackers can use cloning machines to make approximate copies and extract partial information, challenging the security of these protocols. This makes quantum cloning a critical area of study for both advancing technology and safeguarding it. Quantum cloning opens a window into the strange and beautiful world of quantum mechanics, where the impossible becomes a challenge to innovate. The no-cloning theorem isn't just a barrier, it's a gateway to understanding the fundamental limits of nature and pushing the boundaries of technology. I encourage you to explore further. Dive into the works of pioneers like Wouters, Zurich, and Buzek to see how their discoveries shape our understanding. Experiment with quantum simulators online to visualize qubits and superposition. Think about how quantum cloning could impact your field, whether it's cybersecurity, computing, or even philosophy, as it raises questions about information and reality itself. The quantum world is full of mysteries waiting for you to unravel, so keep asking questions and chasing the unknown. What a thrilling journey through quantum cloning. We've explored its definition, the no-cloning theorem, various cloning methods, and its impact on technology. Now, I want to hear from you. Drop your thoughts, questions, or video ideas in the comments below. Have you ever thought about quantum mechanics before? Share your insights. If this video sparked your curiosity, give it a thumbs up, subscribe, and hit the bell for more mind-bending content. Let's keep this conversation alive and inspire each other to explore the quantum frontier. Until next time, stay curious, and I'll see you in the comments.